Welcome back to Eli UW. Today we're going to be studying eigenvalues and eigenvectors. And I'll do an example for a 2x2 matrix, and you'll see that doing it for larger matrices like 3x3, 4x4, it just ends up being having to compute a determinant for a larger matrix. So I might do a video on doing determinants of larger matrices, as it's Cramer's rule and stuff like that. But for now, we'll do a 2x2 example, and you can get the idea. So let's just do some definitions. If I say V, that'll be an eigenvector. If I say lambda, that'll be an eigenvalue. And A is a matrix, and it's a square matrix. There are methods for finding eigenvalues when you find the eigenvalues, it's also called diagonalizing, because the eigenvalues the eigenvectors represent a basis in which the square matrix has values only along the diagonal and zeros elsewhere. So there are methods for non-square matrices. They're more complicated. It's called singular value decomposition. We're not going to cover those. For most of the nice matrices, they'll be square. Hopefully in your examples they'll be square. So the equation, our master equation we want to satisfy, is AV equals lambda V. So if a matrix is diagonalizable, if it has eigenvectors and eigenvalues, it satisfies this funny equation that means if I multiply the matrix by a vector, I'll just get back a scalar times that vector, right? Lambda is just a number. It's 1, 2, 3, 4, 5, negative 1, 2, or whatever, right? So let's do an example. And I'll, as I go along, I'll tell you some more equations that you might need to know. So we'll use this matrix 1, 1, 1, 1. Pretty simple. So the first step is we have to solve determinant of A minus lambda times the identity matrix equals 0. Okay? For a 2x2 matrix, so we'll say this matrix B is A, B, C, D. Determinant of B is AD minus BC. It's pretty easy. For 3x3 matrices, this rule doesn't work. It's different. So the first thing we're going to do is just compute what's inside of the determinant. We'll do this slowly. So first we're going to do A minus lambda times identity, right? So we leave A alone. It's 1, 1, 1, 1. Minus this lambda times the identity matrix is 1, 0, 0, 1. Right? And so you get 1 minus lambda, 1, 1, 1 minus lambda as our answer. So we want to find the determinant of this and equate it to 0. So first let's find the determinant. Right? Using this equation right here, this is 1 minus lambda squared minus 1. Right? I just did these two multiplied minus these two multiplied. I'm going to expand this squared term, right? I'm going to get lambda squared minus 2 lambda plus 1 minus 1, right? These guys are going to cancel. And so I'm going to get lambda squared minus 2 lambda. And now we want to set this equal to 0. So determinant of A minus lambda times the identity equals 0. This is the same as lambda squared minus 2 lambda equals 0. All right. So now we're going to just factor like we would in high school. Right? Pull out a lambda. We get lambda minus 2 equals 0. So our first eigenvalue is the eigenvalue of 0. No one ever said that lambda couldn't be 0. That's fine. And our second eigenvalue is lambda equals 2. Right? So now we've done half the work. We found the eigenvalues. That's usually the easier part. Right? Now the next thing to do is find the eigenvectors. And to do that, we're going to plug into this equation star, our equation that we have to satisfy. All right, so we have AV equals lambda V. So first we're going to do it for lambda 1 equals 0, right? So this lambda 1 is 0, so we just have A times V. So let's plug in what we have. V is just a vector, right? So I write V as a vector with components V1, V2. You could write V as a vector with components XY. You could write it as, components ZW. It doesn't matter, right? But it's a vector with 2 components because we have a 2x2 matrix. If we had a 3x3 matrix, V would have 3 components, right? So let's compute this. So we have 1, 1, 1, 1 times V1, V2 equals 0, right? And so, we're each equation will give us the exact same thing. So we just can use the top line. So multiplying this out, we would get V1 plus V2 equals 0. And that's just using matrix multiplication, right? This is a 2x2, and this is a 2x1, so they're okay. So now we just have to solve this equation. So this means V1 equals minus V2, right? That's the only way for V1 plus V2 to equal 0. So then you just have to plug in something for V1 and V2, for just one of them. So for just V2, let's say. So I could say, let V2 equal 1. That means V1 equals minus 1, because V1 is minus V2. So our eigenvector V, we'll call eigenvector lambda 1, is minus 1, 1. Simple. Okay? Also note, eigenvectors are not unique. Not. And you can see that because, you could have chosen V2 to be minus 1 here, let's say, and then we would have had the eigenvector 1 minus 1. Or you could have chosen V to be 2, then we would have had the eigenvector minus 2, 2. So they're not unique. So for lambda 2 equals 2, we do the same thing, right? So now our equation becomes AV equals 2V, right? So let's compute that. We have 1, 1, 1, 1 times V1, V2 equals 2 times V1, V2. Again, I'll just use the top equation. Could have used the, this bottom equation, same thing, right? So using the matrix multiplication, we would get V1 plus V2, same as this left-hand side before, but now we have equals 2V1. If I had done the lower equation, I would have gone V1 plus V2 equals 2V2, but we did the top equation. So again, we're going to solve for one of these. So we can have V2 equals V1. I've just subtracted V1 from both sides. So they're equivalent. So again, I'm going to let V2 equals 1. That means V1 equals 1. So our eigenvector for lambda 2 is 1, 1. And that's it. We found all the eigenvalues and all the eigenvectors of a 2x2 matrix. As I said, doing this for 3x3, 4x4 matrices, all you have to do is, study how to determine a determinant of a 3x3 matrix. And so maybe I'll see you later on to do that. Thanks for listening, guys.